Different hearts, different dreams. Injective souls ignite the beams. No dream alone, no path ignored. Surjective wills knock every door. More hearts to thrive, or more dreams to grow. Two mighty sets now march toward battle. The wings of cardinality raise us high to the heaven of infinity, beyond the sky.
We have previously discussed the idea of understanding a set by examining its relationships with other sets, typically through the construction of functions. A natural and fundamental question one might ask about a given set is, how many elements does it contain? Somewhat unexpectedly, the answer to this question also relies on functions, viewed through the lens of injections, surjections, and bijections. Look at the figure. What is the first thought that comes to your mind? Most would say, without hesitation, there are 3 apples. Of course, that is correct. But pause for a moment. What does that statement actually mean? The term number of elements in a set seems like common sense, but upon reflection, it turns out to be an ambiguous idea. After all, what are the numbers 1, 2, and 3? They are merely abstract entities, represented by conventional Arabic symbols. The act of counting doesn't rely on any special property of the apples, nor on the symbols themselves. It has nothing directly to do with either of them, and yet it depends entirely on both. Indeed, it means that we can establish a bijection between the set of apples and the set 1, 2, 3. Counting is precisely the act of building a bijection from one set to another set. While switching from counting to constructing bijections is a natural move, it may not always align with our intuition. For example, if there are only 3 yarn balls but 4 cats, then one cat, say, our poor black cat on the left, will inevitably be left without a yarn ball to play with. However, when dealing with infinite sets, our usual intuitions no longer apply. Suppose there are infinitely many cats standing in a row, each with a yarn ball to play with. Now imagine the black cat arrives as a newcomer. Can we still arrange things so that every cat has a yarn ball? Surprisingly, the answer is yes. Simply let the black cat take the yarn ball originally assigned to cat number 1. Then, let cat number 1 take the yarn ball of cat number 2 take that of cat number 3, and so on. Each cat plays with the yarn ball of the next cat in line, as if all the yarn balls have been shifted one step to the left. In this way, every cat, including the newcomer, ends up with a yarn ball. Fantastic! This is just another version of the famous Hilbert Hotel idea. Note that this shift map can be described as a function from the natural numbers to the positive natural numbers, defined by Fn equals n plus 1. This means the nth cat is assigned the yarn ball originally handled by the next cat. In particular, we have established a bijection between the set of natural numbers and a proper subset of itself. A situation that is only possible for infinite sets. Now we introduce the definition of equinumerosity. Let A, B be 2 sets. We say that A and B are equinumerous, or alternatively, that A and B have the same cardinality, if there is a bijection F from A to B. We use 2 vertical bars around a set to represent the cardinality of it. In the context of the previous example, we observe that the set of natural numbers and the set of positive integers have the same cardinality, since the shift map that sends n to n plus 1 defines a bijection between them. We end this section with an example of both theoretical and historical interest, commonly known today as Galileo's paradox. It was first discussed in Galileo's 1638 work, Discourses and Mathematical Demonstrations Relating to Two New Sciences, the last book he published. Let S be the set of all perfect square numbers, that is, numbers such as 0, 1, 4, 9, 16, 25, and so on. Clearly, this is a proper subset of the natural numbers. Yet, consider the function from the natural numbers to S, defined by sending n to n squared. This function is clearly a bijection. As a result, S, although a proper subset of the natural numbers, has the same cardinality as the natural numbers. Galileo had already recognized the subtlety in comparing the sizes of infinite sets, remarking, "The attributes equal, greater, and less are not applicable to infinite, but only to finite quantities." Keeping his insights in mind in the next few sections, we will explore how to carefully compare the cardinalities of sets, especially infinite ones.
신라 텐세